Now we move on to talk about conditional probability within the context of a simple example. And at the end of this, then I'll introduce the mathematical equations that we can use to calculate conditional probability. A probability that is based on part of a sample space is called conditional probability. So very important to realize we are looking at a part of the sample space and not the total sample space. So if this is the total sample space and you have, say, events A and B, if you wanted to calculate the probability of event A, then we'll grab the number of outcomes in A, right, K, and then divide that by N, where N is the total sample space, all of this rectangle. If for some reason we are dividing by the number of outcomes in B instead of N. So we are dividing by number of outcomes in B, let's say KB, whatever you choose to use. To call the number you're dividing by instead of dividing by N, then what you're looking at is a conditional probability. Why? Because you're looking at the outcomes given that B is satisfied. And because we already know that we have B as an outcome, then you're going to be dividing by that. The sample space has been reduced from this massive set of all possible outcomes to only this smaller shaded area. And that implies we are looking at a conditional probability. It is given that B was the outcome. So let's talk about that within this example. You have a table that gives the specifications for the length and diameter of 1,000 rods. The number of rods with different classes of lengths and diameters are given. So we have lengths and we have diameters. For the length, it's either too short, too long, or the length is just fine. The diameter, same deal. It's either too thin, too thick, or the diameter is just okay. And then we have numbers corresponding to the combinations of the lengths and the diameters. So number of rods that are too short and too thin is 10. Number of rods with the right diameter and the right length is 900, and so on. So first question, what is the probability that the diameter of the rod is okay? So where is diameter? Is it on the X or the Y axis? Diameter is on, this is it. These are the diameters. They're either too thin, okay, or thick. So we're asking for the probability that diameter is okay. So we're looking at this column basically. So again, it's K over N, right? So what's K? All possible outcomes for this event that the diameter is okay. So that's 3 plus 900 plus 25. That's K. So what is the total number of outcomes? 1,000 rods. Or add up everything. Add up everything is 1,000. That's the total number of outcomes. What just happened? It's no more right here. Okay. And so that is the probability that the diameter is okay. And this probability is called unconditional probability. Why? You're dividing by N, which is the entire sample space, which is what I tried to explain here. But obviously, explaining it within a context of the probabilities makes it easier. So we move on to the next slide, a different question. Assume that a rod is sampled and the length is okay. Now, what is the probability that the diameter is also okay? So you are given that the length is okay. That's the starting point. So where is that? Where is the outcomes for the length being okay? This is length. It could be too short. It could be okay. belong. So when it's okay, you're looking at what I have selected in red, right? Good. So you are given that. Now, what is the probability that the diameter is also okay? Meaning, what is the probability that the diameter is okay given that the length is okay? So this is the diameter being okay, is this column. So what outcomes do we have at the intersection between this and the previously shaded one? So what's K? If you are given that the length is okay and then diameter is okay. So for the diameter to be okay, you have to be in this column. And that takes you to only 900, right? Because you are within the OK column for the length. So K is 900. Now, what is the reduced sample space? Because you are given that the length is okay. So you're not going to divide by 1000, right? You're going to divide by the sum along this row, which is 38 plus 900 plus 4. So that is conditional probability, and we can write it as probability that length is okay. Given, this is how you write given that, it's probability that the diameter is okay. That's the question. So probability that diameter is okay, given that the length is okay. So that's how you write that. Will be 900, which is diameter being okay, that intersects with the length being okay, 900, divided by all possible outcomes when we already know that the length is okay, and that's 38 plus 900 plus 4, which is what? 942, right? Now you use your calculators and finish up the calculation. So it is important to realize that the condition that you are given here, which is that the length is okay, reduced the sample space from 1000, which was everything, to just the sum along this column, which is 942. So out of this 942, only 900 of them have their diameter being okay. And that's why 900 is K, and 942 becomes the new N, right? That has been reduced. And that's the conditional probability that the diameter is okay, given that the length is okay. And this is different from the probability. Better still, I should say, this is different from the unconditional probability that diameter is okay. So whenever you don't have that this vertical given sign, then you're looking at an unconditional probability, sometimes referred to as marginal probability, because there is no condition. Good. So probability that the diameter is okay by itself, how will you calculate that? You come in here and grab the entire column. That's probability that the diameter is okay. Those are all the outcomes, right? So it's 3 plus 900 plus 25, which is 928, and you divide by total number of outcomes, which is 1000, because there is no condition. So you're dividing by n, which is the entire sample space. So it's different. Another question. Find the probability that the diameter is okay, given that the length is not too long. Sorry, given that the length is too long. I know why I said not too long. So probability the diameter is okay, given that the length is too long. So we start out with the condition that the length is too long. So this is the length, this is too long, you're sitting in this column, in this row. This is a row. So you're sitting in this row. Where is K when the diameter is okay? So you're in the middle still. And then that means you only have this as your K. So K is 25. And what's your reduced space, right? You're not looking at the entire sample space. the sample space is reduced to the condition when the length is too long, which is this row, which is 2 plus 25 plus 13. And then whatever that is probability that the diameter is okay given that the rod is not too long. This is what we calculated here. So 40 is this sum, is the number of outcomes that satisfy this condition that the rod is not too long. 25 is the number of rods that have the right diameter and obey the condition that the rod is not too long. Now we will work out what the equation is for this conditional probability using this case study. So this is 25 divided by 40, right? Well, what if we divide top and bottom? So I can write it in put it here, 25 divided by 40. What if we divide top and bottom by 1000? Right, that leaves the fraction unchanged. Then think about this. What's 25 divided by 1000? It's an unconditional probability, obviously, right? Because you're dividing by 1000. So it's this number divided by 1000. And what's this number? Is the probability that diameter is okay and, right, and is intersection, length okay. So what if we make it more succinct and use D for diameter? D okay, intersection and length okay. That's what this numerator is. How about this one? 40 divided by 1000. What's 40? 40 was this sum, right? Sum along this column. And that's probability length is too long. So probability length, I'm just going to use arrow. That's it. It's the unconditional probability of length too long. And this is basically what? Probability. This probability we're looking at. Diameter okay, given that length is too long. Given length too long. So you can write this conditional probability in this form. So if these are events A and B, we can say probability of A, so A is diameter okay, given length too long, equals probability D is what? Is A, D okay is A, intersection L okay, intersection of length okay divided by probability. This can be length okay. This has to be length too long, right? Yeah, this is length too long. Why? It's 25 over 1000, right? What's 25? It's probability that the diameter is okay, given that the length is too long. That's 25. If you say given length okay, then you're looking at 900. So that was a typo here. This is length too long, and that's why it's probability A intersection B divided by probability length too long, which is B. So this is your expression for conditional probability, which you basically derived empirically from this example. And when you check out that here, this is what it looks like in this form, which I also show here. And I'll talk more about this in the next video.